Support vector machine, or SVM, is one of those machine learning algorithms that may sound technical at first, but at its heart, it's all about drawing a smart line to separate things that belong in different groups. Imagine you're trying to decide whether a customer should buy flight delay insurance. You have some information about them, what airline they're flying, what the weather looks like, the time of day, and how often flights to their destination get delayed. Now, picture this information laid out on a graph. Some customers, based on past data, ended up buying the insurance, others didn't. What you need is a way to separate these two types of customers so you can predict what a new customer is likely to do. This is where SVM shines. It tries to draw the best possible boundary between the two groups. But not just any boundary, it looks for the one that creates the widest possible gap between the closest points of each group. These crucial edge points are called support vectors, and they're what the algorithm uses to anchor that dividing line, or what's technically called a hyperplane. In a simple two-dimensional example, this hyperplane is just a line. Imagine it like a street running between two neighborhoods. The wider the street, the better, because it keeps the two sides clearly apart. The magic of SVM is that it doesn't just stop with two dimensions. If your data has many features, 10, 20, or even thousands, SVM can still find that perfect dividing surface in a high-dimensional space. But what if the data can't be separated by a straight line? Let's say your customer's behaviors are more tangled, and the boundary is curved or complex. SVM has a powerful trick for this. It uses something called a kernel function to transform the data into a higher dimensional space where that clean separation does become possible. It's a bit like folding a piece of paper to make two dots that were far apart suddenly touch. This ability to handle nonlinear patterns makes SVM extremely flexible. Of course, like any tool, it comes with strengths and limitations. On the plus side, SVM works very well with high-dimensional data, where there are more features than samples. It's also memory efficient, because it only cares about the support vectors, the key points that define the margin. And when the data is well behaved, meaning the classes are cleanly separated, SVM can be remarkably accurate. But it's not perfect. If the data is noisy or overlapping, meaning there's no clear line between the groups, SVM can struggle. It also tends to slow down on very large datasets, and requires careful tuning of parameters like the type of kernel used, or how much you're willing to tolerate misclassified examples. Despite these challenges, SVM has been widely used in many real-world applications. Email systems use it to decide whether a message is spam or not. Banks rely on it to predict loan defaults. Healthcare systems may use it to detect diseases based on patient symptoms. And yes, it can even be used to recommend flight delay insurance to customers based on flight and weather conditions. At its core, SVM is about making clear, confident decisions by drawing the right boundaries, even when the data is messy or the dimensions are high. It's one of the many tools in the AI toolkit that helps businesses make smarter, faster predictions.